Hey, hey, all right, students. Hey, welcome back, and online students and in-person students, and we're getting closer and closer to the end here. We've got one more lecture here on optics, and so here's my plan. My plan is to wrap up optics today no matter what happens, and that way, starting on week 5, we can get into the last part of this course and last part of summer school, which is the modern physics stuff. And so I was telling the in-person people yesterday, and so I want to tell you online people, we won't get a chance to cover everything in chapters 26 and 27, so I'm just going to pick some important quantities or some topics that I think are the most important related to you guys in the life science. And that's where I want to jump in then. And so the first half of this lecture before the break, let's look at chapter 26, and then after the break, let's look at 27, and we'll just see how far we get by the time we finish all this. So here's my game plan. It might be a little bit over ambitious, so we might not even get this far, but here's what I'm hoping. I'm hoping that in this chapter, chapter 26, I can show you some nice life science related stuff. And so I want to do sections 26.1, 26.2, and 26.4. Okay, and those will be the limited topics. And so you'll see when you look at the book, there's 6 sections, and we're going to do 3 of the 6 sections. So we're going to do about half of chapter 26, and those will be the ones that, you know, I would be on the exam. Know that I would not test you on anything that was in the other sections that I didn't get a chance to lecture on. It's hard enough to learn it just on your own reading. And so hopefully you're doing both. Hopefully you're listening to me lecture, and then you're also doing the reading, and that makes it sink in a little deeper. Plus, we do a lab on it. So that's the first thing I want to say, is that we're going to do these 3 sections. Then when we get to chapter 27, which will probably start after the break, I want to look at sections 1 and 2, kind of give you the foundation, so we need to really focus on that. And then sections 3 and 4 kind of fit together in what's called the Young's double slit or a diffraction gradient one. And so we'll look at that. And then we'll jump over to polarization and do examples from each one. So that'll be the second half. So it looks like we'll a little ambitious and try to do 5, but like I said, this is kind of the basic, these kind of group together, and that's kind of my thinking that we would have enough time. Well, let's see what happens here. All right, so as I begin here, let me begin by first showing you a picture or a diagram that actually goes back to the last chapter. And let me make it a little smaller so I can go a little faster here. But it's figure 34, and it goes into great detail here about lenses and cameras, and particularly the camera and the human eye. Let's see, 34. It's further back maybe than I gave it credit. It's got to be, there it is. And in this one, this will give me a chance to remind myself and remind you that in addition to the lecture I sent out on this chapter, which is 25, I followed it up with a supplement. That's more for you guys on the in-person part, because at the end I said, oh, sorry, we're out of time. I don't have time to do any examples using those equations. But I was able to put together about, I think it was a 38-minute little video. I did 5 examples, and hopefully you'll get a chance to look at that. And so all of you, in person or online, after you see the lecture from 25, actually look at those examples. But I thought doing this section and these 3 sections would actually help with that, because I want to put a very important equation from chapter 25 here on the board. 2 of them, actually. And so we said that if you take the reciprocal of the object distance and the reciprocal of the image distance, that is equal to the reciprocal of the focal length. The other important equation is that the magnification is the negative of the image distance over the object distance. And it's these two basic equations that I was saying work for both the lenses and the mirrors. And each of those have 3 cases. And so you can say in all 6 cases, 3 cases for the lenses, 3 cases for the mirrors, this should work. And so I use this equation a lot in that supplemental lecture. And so I want to pick up today with these equations, and so I think this will help you digest those equations. Now, I probably should give you one more equation. I put it in the supplemental lecture. You guys who are in person, sorry I didn't mention a very important equation, or at least more of words. It's not a hard equation, but sometimes people refer to lenses or mirrors by their power, not by their focal length. And so if you say their focal length or their power, you're saying one and the same. And the reciprocal of the focal length is called its power. And so you'll see that terminology used frequently, especially in this chapter we're about to do. And so I'll throw that third equation in there. And this one's, like I said, pretty straightforward, and I addressed it in the supplemental part here. But it's these two pieces that I want to focus on. And the start of this chapter, chapter 26, and the reason I picked this first one is it goes into a little more detail about the human eye and how optics work for the human eye. And since you guys are life science, I thought that would be real important. But I think also to have an understanding of the human eye, we have to contrast that with the camera. So I'm going to start with a diagram from chapter 25, which shows both the human eye and the camera. And there is a slight difference between the two, and that's what I want to focus on. And I think the camera is a little bit easier, so I'll start there. And so if you look at this diagram of the camera, here is the object. So here is a person. This is the camera, so there's a lens in a camera. And then there is a film, or a CCD array. And the goal of the camera is to get the image on the CCD array and to get it in focus. What's interesting about the camera is that for a camera, the focal length is fixed. Well, you might say the power is fixed. The focal length comes from the curvature of this lens. As we were talking about in 25, we curve this lens. And that gives it a certain amount of power, a certain amount of focal length. You can kind of see, I'll call this is the case number 2, where the object, and so if you're looking at my eye here, you know, my object is closer than the focal length, and so it makes it bigger and right side up and appearing to be on the virtual side. And so that's what we called case number 2. Now, for a camera, we want case number 1. We actually want the light to go on to the CCD array. But my point is, for the lens in the camera, and I'll just pick on the most common camera, the 35 millimeter camera. Well, that means the lens has a focal length of 35 millimeters. And it's fixed. You can't change it. And so what I'm trying to say here is, because the focal length is fixed, for you to take a picture of something, there's the object distance, since that could vary. You might take your camera and you might take a picture of something close like this faucet, or maybe something far away as I look out the door, that tree down there. And so because this could be different, and this is fixed, we have to have the ability to adjust the image distance. And so what a camera does is you can roll the barrel, and by turning the barrel, there's a little screw that moves the lens back and forth. And so you change the image distance so that the image distance comes out to be the appropriate amount. And so if you're looking at something far away, so this is big, then the image distance has to be relatively small, because the two together have to equal the focal length. And so if I was focusing my camera on that tree way out there, I would adjust the barrel of my camera that moves the lens in, and I would have a small distance for the image. The image distance is from the lens to the film or to the CCD array. On the other hand, if I was trying to focus on something close, so like this faucet, I would then roll the barrel, and because my object distance is now small, my image distance has to increase. And so for me to get it into focus, I would roll the barrel and then the lens would move out, and that would give me a larger image distance. The image distance would be the distance from the lens to the back of the camera where the film or the CCD array is. So that's kind of the basic thinking in terms of our optics for a camera. I want to change our attention to the human eye, and that is section 1 here of chapter 26. And so the human eye, the function is a little different. Now, it's still a lens, it's still an optical system, and so this is what your author is trying to contrast down here. He says that when you're using the human eye, or I shouldn't even say human, I should just say the eye, because there's all kind of species that works basically the same way, is the light comes in and has a bending, a refraction. There's a lens effect. I guess technically it is 2 effects. One is the curvature of the cornea. In fact, most of the focusing is actually done by the cornea itself. That's kind of fixed. That can't be changed. But then the second part of the eye is the lens in the eye. And the lens in the eye is squishy. You have these little muscles around the lens that push in. And when they squish the lens, they make it a little fatter, if you will, more curvature. And more curvature would mean a smaller focal length or a higher power to it. And that's the difference, an important difference between the camera and the eye. Because a camera, you don't change the focal length, you change the distance. But the eye, what you do is you change the focal length, but you don't change the image distance. And so the image distance is the size of the eye socket. And for humans, you should know that that's about 2 centimeters. And so as we do some example problems, know that if we're talking about an image formed from the eye, and here is where I should say human eye, the human eye has a depth of about 2 centimeters from the lens to the retina. And so we always want our image distance to be 2. So here is the part I'm trying to say here. That as we talk about our optics and we apply it to the human eye, I would say what's fixed is the image distance. So let me rewrite this equation as something like this. 1 over the image distance is 1 over the focal length minus 1 over the object distance. And let me think of the equation in this pattern, because now, like I said, this number is going to be our 2 centimeters. And so just know that every time we talk about the human eye, it's 2 centimeters. Image distance, 2 centimeters, 2 centimeters. Now, I know that's not perfect. Some human eyes are a little bigger than others, but really not by much. Even a big person and a small person have relatively the same size eye. I don't know if that, I was going to say eye socket. I don't think that's the socket, but the depth of the eye, the internal mechanism of the eye, the distance from the lens to the retina seems to be about 2 to 2.1 centimeters for all humans. So there's not much of a variation. So keeping that in mind, we're just going to say if it's a human eye, a big person, small person, young person, doesn't really matter. We're just going to say this is the image distance. Now, here's why that matters. That matters because then, for the human eye to function, there's going to be different object distances. I could stand here, and again, I could use my eyes to focus on the sink, but I could also use my eyes to focus on that tree. And so if I focus on the tree, I would say the object distance is really big. Now notice the minus sign here. So if object distance gets big, focal length has to get big. They go together. They don't battle each other. Remember, when the camera, they battled each other. I was adding them two together. So if one is big, one is small, that has to equal the constant. But here the math says the reverse. The math here is saying when you have a big object distance, right, you have a big focal length, or I should say the biggest it's going to get. And so I will say that for the human eye, I would like my human eye to focus, now maybe I'll write it this way, on objects that are really far away, I'll put infinity, up to some limit. And every human then was going to have this limit, because watch what happens. Watch what happens as an object gets closer and closer. And so if I was looking at that tree, and then I looked a little closer at the building, then I looked a little closer at the wall, then I looked a little closer at the sink here, or faucet, then what I would be doing is I would be saying, I'm looking at objects that are closer and closer and closer. That means smaller and smaller and smaller. So that means the focal length has to get smaller and smaller and smaller. And so the human eye is doing this. The human eye then is using these muscles to squish the lens, to make the lens more bowed, more curved. The more curved it is, the more it bends the light, the more powerful that lens is. So that's the last chapter. That's why people can get tired, people can get headaches when you spend a long time, say, studying and reading a book, because the book is, maybe 30 centimeters away, and in order to focus on those letters, you have to have a small focal length. And to have a small focal length, you have to squish that lens. And in order to squish that lens, you got to use your muscles. And so your muscles actually work. And so what's called the relaxed position of the eye is when I'm looking at something far away. And so many people recommend study habits that, okay, you study for a given period of time, maybe 20 minutes. Maybe every 20 minutes, stop, look at something far away, maybe look at that for 5-10 seconds, and just relax those muscles. Give them a break. Say, oh, okay. And you can just kind of look off into the distance. Now the muscles are relaxed. Maybe they gain some strength. All right, and then you get back into studying, because obviously you need a lot of time studying. So you got to get back onto it. So, but that's the working on it. It's why in modern times so many people like myself wear corrective vision because we've spent so much time. I didn't start college wearing glasses, but I finished college wearing glasses because these muscles are pulling in so tight. And as they pull in so tight, they pull in the eye socket, and now I've become slightly nearsighted. My cornea has more curvature than it should have, and that it originally had. And that was the strain of the muscles. And so with people living lives more indoors than they did 100 or 200 years ago, more people are now nearsighted, and I'm one of those. Well, I'm sort of getting into section 2, because section 2 we're going to talk about what can go wrong with the eye and how do you correct it. And so we'll talk about my vision and Ron's vision here. I got his glasses, I got my glasses, and we'll do some talking more about that. Well, let me use this as an opportunity to then scroll back to this chapter, the start of this chapter, because your author does even a better job with the human eye here in this first section of chapter 26, and he's got a bunch of different pictures of the human eye. You'll see that one I just had there, and there is a better picture, and even names the different parts of the muscles and the fibers and the aqueous humor and the retina and the optical nerve and all those good things. Well, let me kind of point out then, as we're talking about this, see, here is inside the eye. And so as we go from air, one, into the cornea, there's a significant change in index. And that's why I was saying most of the focusing of the eye is the cornea. He said, okay, I'm going to do that. The last little bit of it is then the lens. And so the muscles in my eyes allow me to control just enough in order to vary that. In fact, here's kind of a fun little first, I guess, step here. I might ask myself, what is the power of the lens, the human eye lens, for these different positions that I want to use my eyes to focus on? And so I already mentioned here that on the far end, I want to look at things far away. Now, on the close end, we often say that we would have then a near point. You know, what is the closest I can see? Because again, if I kind of go back to this picture of the human eye, yeah, I'll use this one. Well, no, let's go this one. This one does a good job of saying, look, if I'm looking at something very far away, the light is nearly parallel coming in, and because of that, I have a small power to the lens, or a big focal length. And I form the image back here on the retina. And so they show a little upside down tree here. And so this person is looking far away at a tree. And so you might ask yourself, okay, what is the power of the lens or the focal length of the lens when you're looking at something far away? And so my first calculation would be, all right, let's solve this equation. And so I'm going to go 1 over, and I'll put 2 centimeters for the image distance. So again, I'll point out, we're talking about a human eye, so it's got to be 2 centimeters. I'm trying to find the focal length, and I'm looking at something that is really far away. I won't even give a number. I'll just say it's really, really big. And then, of course, what's nice about that is, what would you call 1 divided by a big number? 1 divided by 1,000,000, 1 divided by 1,000,000,000, 1 divided by 1,000,000,000,000. Yeah, I'd say that's pretty much 0. And so then I would get something like 1 over 2 centimeters equals 1 over the focal length, and so the focal length is 2 centimeters. And so I would say my eye, if my eye didn't have problems and I needed glasses, but without glasses, somebody who doesn't wear glasses, if they look at something far away, the light doing something like this, the muscles relax, the lens gets in its relaxed position, and between the cornea and the lens, it forms an image 2 centimeters right on the retina, and so I can be relaxed and I can look out at the mountains or the trees, and I'm all in a relaxed position. That is the biggest the focal length could be. or you might say the lowest the power can be. And so if I go to calculate the power, which is 1 over the focal length, and it is tradition then to do the power in units of meters. And so, let's see, 1 over 2 is 50, or 1 over 0.02 is 50. And you might even say 50 inverse meters, and hopefully you got a chance to see my little discussion on that supplemental problem, that 38-minute I added to yesterday. And so some of you guys are saying, hey, I saw that. So that's from yesterday. So, but the reciprocal of that is the power, and if you measure the distance in meters, that is measured in diopters. So I would say for the human eye, doing my first calculation, the relaxed position gives 50 diopters. That's the relaxed position. Now, as we look at something a little closer, the eyes have to, the muscle has to squish down on the lens, giving it more curvature, and like I said, that makes it more powerful of a lens, or a shorter focal length. It's again why I would get tired after a while, might even get a headache after a while by focusing on something close. Everybody then is going to have what we call a near point, because everybody has a limit to how much their muscles can squish down. And so it looks like here they're kind of showing maybe somebody looking at something small. They got what looks like a button to me. And so it kind of looks like the author's thinking about somebody doing some sewing, and they take a button and they get it real close so they can thread the needle through the button or something. But because they're so close, the muscles have to squish down, making more curvature to the lens, making the focal length smaller, or the power a little greater, in order to get it focused. And then everybody's going to have a limit. There's going to be a place where your muscles and your lens just can't squish down anymore. And so it's kind of fun to maybe take some small writing, like right here, and get, okay, I can read it, I can read it, I can read it, I can read it. Oh, nope, blurry, can't read it. And so at that point, your limit has come. Now you guys are young and healthy, so your near point is going to be a lot better than mine, but that's why, older people, just, can't see close. They keep moving the newspaper or the magazine further away. And usually when it gets about arm's length is when people finally decide to get reading glasses. They're like, okay, oh yeah, I definitely need glasses. I can't get my book far enough and read it. Question?
I just wanted to make sure I had this down correctly. So the power is smallest when the focal is 2 centimeters, so the greater the DO, the smaller the power.
For the human eye, yes. Yeah.
Thank you.
Sure. And so your words are great, but I'm going to say something bigger, I hope. Everything you just said was a special case of this equation. All right, so most important is this equation. Yeah. And so what I'm trying to do is, look at this equation as applied to the human eye. This will give me a chance to say, remember, physics is about knowing how to apply a few fundamental principles to explain a universal phenomenon. So I'm going to use this. I could use this for a microscope. I could use this for a telescope. I could use this for a camera. I could use this for a magnifying glass. And now I'm using it for the human eye. And so that's the bigger picture, is that I can use it for anything. But what you said is specifically for the human eye. So, sure. Now, let me go to the other end of this spectrum, if you will, because what we like to say then is kind of a normal range is that humans can see things and focus up to 25 centimeters away. So that's kind of our working number. Now, granted, every individual is a little different. And you guys are mostly young and healthy, so it wouldn't surprise me if you could focus on things closer than 25. And it wouldn't surprise me if I couldn't focus on things as close as 25. My elasticity has just diminished over 57 years. You know, I just don't have that squishability. And just like my skin is old and saggy, my my lenses is hard and hard to squish. Plus, I've probably lost some muscle tissue also. But it's probably more just the hardness of the lens than the weakness of the muscles. Weakness of the muscle will come a little later in life, but the hardness of the lens starts to kick in those late 40s and through the 50s and the 60s. Okay. Well, anyways, I hope you're kind of getting the idea of how the lens and the human eye works, because we want to then follow this with section 2 of then what can go wrong and how do we correct it. So why do we wear contact lenses? Why do we wear glasses? Now, I do want to do this calculation. Let's ask ourselves, what would be the power of the human eye when we are focused on something as close? And let's use the 25 centimeters. So doing this same equation, I would say 1 over the focal length is 1 over the object distance plus 1 over the image distance. And so now I'm going to put something, and I'll go ahead and use meters, 0.25 meters in front of me. So maybe I'm reading a book. And so that's the object distance. Now remember, for the human eye, the image distance always needs to be the 2 centimeters, which I will write in terms of meters. Right? And so I need my muscles to squish my lens to make more curvature, to lower the focal length or increase the power in order to bring this into focus. And there it is. My image distance needs to be 2 centimeters. So if I grab my calculator here, I can say, all right, what would the focal length be now? And so let me go 0.25 reciprocal plus 0.02 reciprocal, hit enter, and that is 54 inverse meters, which is 54 diopters. And if I now take the reciprocal of that, I get a focal length of 0.0185. And so it's not a big change in terms of the power or the focal length, but for my human eye to work well, for me to focus on things as close as 25 or as far away as I desire, my lens needs to change its focal length from the longer 2 centimeter down to a shorter 18.5 centimeters. So that slight variation in focal length allows me to focus on a huge range of distances. And that's the general principle. In fact, before we get to section 2, let's look at 2 examples, number 1 and number 3. And I might have actually just did number 1 here. Let me come over here and go to page 1174 and look here then at the start of the problems, number 1. No, I guess I didn't. No. Okay, good. I'm glad I did those calculations because that's helpful too. But let's do number 1. Number 1 says, what is the power of the eye? And I think they mean human eye here. What is the power of the eye when viewing an object that is 50 centimeters away? Well, this is kind of really that same calculation, but my position here of my eye is looking at something that, and I'm going to put it as a 0.5 meter. So it's not as close, but it's not as far. So as we said, something close, you need a power of 54 diopters. Something that is far away, you need 50 diopters. This is something in between. So I'm just going to say it's somewhere between 50 and 54 diopters is the power of this one. But I do want to point out again that the image distance is not listed in that problem. This is the part you need to know, that the human eye is going to need 2 centimeters for the image distance. So grabbing my calculator, I can go 0.5 reciprocal, add 0.02 reciprocal, hit enter, and that comes out to be by itself 52 inverse meters, that is 52 diopters. And that's the power. The focal length then, of course, is the reciprocal of that. And so it looks like a focal length of about 19.2 centimeters. Nope, wrong decimal. 1.29 centimeters is the focal length. And so this is kind of somewhere in between the 2 extremes that I just calculated. And it makes sense. And so again, that human eye, the power is somewhere between 50 and 54. I'm looking at something kind of in the middle ground. So the power of my lens focusing on something a half a meter. Let's see, that's probably this box right here, half a meter. Okay, my lenses make a power of 52 diopters. All right. And if I look at number 3, and I want to keep saying the same thing, that it's this nice equation that works for all the lenses and all the mirrors. Of course, when we set up a lens and a mirror, we've got those 3 cases we talked about, case 1, case 2, and case 3. And so we got to remember sometimes we get negative numbers. Right now we're doing all case 1 stuff, so all positive numbers here. But if I was trying to solve this problem, I guess the first thing I would write is 1 over the object distance plus 1 over the image distance is 1 over the focal length. And the magnification is negative the image distance over the object distance. So those are my 2 fundamental equations here. Let's see what this one has to say. It says the print in many books is about 3.5 millimeters in height. So if you're reading a book, you can look at the letters, they're about 3.5 millimeters in height. How high is the image of the print on the retina when the book is held 30 centimeters away? Okay, and maybe I should make it a little bigger. Is that what you're trying to say back there, Ron, for the camera? All right. So let's see, how high is the image? So they're really asking a magnification here. So I don't even know if I need this first equation, because if I ask for the magnification, I guess the first thing I would do is say, well, since this is the human eye, I know that the human eye is going to adjust the focal length of the lens so that the image distance is 2 centimeters. If it's not 2 centimeters, it's not in focus. So that's where the retina is, 2 centimeters. So I'll say it again, every time we're dealing with the human eye, we know the image distance, 2 centimeters. All right. Now in this case, we determine where we hold it, and it sounds like we're going to hold the book 30 centimeters away. And of course, when you take a ratio, you could do it in meters or inches or centimeters or miles. Doesn't really matter. They cancel off. So I won't bother to switch this to meters. I'll just leave it the way it is. And it looks like I get a negative 1/15. So again, this is case number 1. So not a surprise that it's negative. So that means the image is going to appear upside down. And I guess I shouldn't even use that word appears upside down. I would just say the image is upside down on your retina, but that doesn't mean it looks upside down to you. Those just stimulate nerve endings, and then it all becomes part of biology. And I've heard people say kind of the weirdest things. Oh, we view the world upside down. Well, the image is upside down on your retina, but then it all turns into a bunch of electrical pulses. So there's no upside down, right side up. I don't really understand why that's such a big deal to people. It all becomes like digital technology at that point. There is no up and down. There's just information being sent to the brain. But I guess technically, as we saw in that earlier picture, the tree was upside down on the retina because it is a negative magnification. Now it's smaller than 1, so it's actually much smaller, which is fine. Because your retina is made out of a bunch of rods and cones, and they're sensitive and very small, and so you can still make out the details. It doesn't matter that the image is small. You can still see the details of each individual leaf of the tree because your rods and cones are, separated each much. I guess right in the center, I guess there's no rods. There's only cones because cones detect kind of the color part of it. And your author does a little bit of that in section 3, and that's where we're going to run out of time, so we won't do with the rods and cones stuff of that. I'll leave that to your biology class here. But what I'll do then is use this to say that the magnification is the height of the image compared to the object. And so that means if I take negative 1/15 of the height of the object, I will now get the height of the image. All right, so negative 1/15, and then they say the height of the object. The letters have a size. They are 3.5 millimeters. So the object height is 3.5 millimeters. And so grabbing my calculator, I can now say what is the height of the images on my retina. And so negative 3.5 divided by 15. And so I'll leave the negative in there to keep reminding me that the image would be upside down. So if again I'm reading a book and I'm looking at the letter A would be upside down image on my retina. If somebody were to look in my retina, they would see the light there focused. They would see, like looking at a screen, they would see the letters on my retina. They'd see them upside down. And they'd be really small. That's about 1/5 of a millimeter. And so that's what this part of problem 1 is about. Oh, good, they do say something. B, it says compare the size of this print to the size of the rods and the cones in the fovea. And we're back to what I had said earlier. This is kind of what turned me off to life sciences. There's just too many words I couldn't pronounce and read here. And discuss the possible details of observing the letter. And I guess I kind of already mentioned that the rods and the cones, and particularly the center of the eye where there's only the cones where you get the color, they're so small that even though that letter looks small, you could see the letter A. You could see a space between, the writing of it. And you could easily distinguish where there is light and where there's not light. So I won't say too much about it. Although I might do something like this, even though it wasn't part of this problem, but it'll give me a chance to do another calculation here. Maybe I could ask my question about, okay, what is the power of the eye right now? What's the focal length of the eye as I'm reading? And so the problem we just did here, where we were looking at something 1/2 meter away, we had a power of 52. So we're going to be closer. So I think the power's got to be a little greater. Although we got 54 when we were at our near point. So it's probably somewhere around a 53. And so I'll give this a little quick calculation and say, okay, what would be the power of my eye right now? And so I'll go 1/30, but I'll put it as a 0.3 reciprocal. Add to it the image distance, 0.09 reciprocal. Hit enter, and that is 53.3. And so 53.3 diopters would be the power of the lens. So again, unlike the camera, the human eye has this adjustment. We can change the focal length. And so it looks like the focal length would be 1.875 centimeters in this scenario. Again, that's why it kind of can help you relax studying a little bit if the book's just a little bit further away, you know. Muscles don't have to work quite as hard. All right, well, let's go on to section 2 then. And so we kind of led into then, you know, what could go wrong with the human eye is you might have too much strength or power to the lens, or you might have too little, and things don't come out quite in focus. And so section 2 here brings up, you know, the problems that can occur, the imperfections that nature has for your eyes. And of course, then that naturally brings up the corrective lenses then we would use to make up for that problem. So we have to understand, you know, what is wrong with the human eye before we can understand then how we're going to correct it. And there's many problems the eye can have, but to make it simple, your author focuses on first somebody who is what we would call nearsighted. Myopia, I guess, is the science word. So somebody who can see things that are near. Now, somebody who could see things far but not near then has hyperopia. Somebody who has trouble seeing things close up because of age, which we often refer to as elder eyes, has presbyopia. And so let's talk about any of these. And maybe last one is somebody, myself included, might have imperfections in what we call the symmetry of the eye, and so they have an astigmatism. And these are fairly easy to kind of comprehend now that we've gone through the last chapter in terms of what the human eye is doing. And so I'll focus first on myopia, somebody who's nearsighted. We call it nearsighted because that means they can read things that are near. I'm nearsighted, which means if I don't have my glasses on, things that are close by are fine. And so I can work on my desk, I can work in the lab, I can read all the letters on here just fine on this laser. But if I look over that wall, that poster, now those are big letters, so I got no problem with those. But those small letters there, I can't focus on that. I don't know what that thing's trying to say. I'd have to walk over here and say, oh, your safety marshal in this area is... It doesn't say. It's located in room. It doesn't say. So, but anyways, that's what the poster says, right? And so I can see things close, but not far away. And the reason why is my eyes are too bent. They're, you might call, too strong. Actually, I like to say it that way. Yeah, my problem is I'm too strong. That's my problem. But my eyes really are bent too much. My cornea is bent too much. That's what LASIK surgery does. I could go get LASIK surgery, and what they would do is they would reshape my cornea and cut off some of that curvature. And therefore, my cornea wouldn't be as powerful anymore. And like I said, when somebody has too much curvature and their lens is too powerful, they would be able to see things near. Because remember, you're trying to make a powerful lens when things are near. The reason I can't see things far away is because when my muscles relax and my lens goes kind of as flat as it will go, my cornea still has too much curvature to it. And it bends the light too much, and I can't get those things far away into focus. And so I see things close, but not far. Hence, I'm nearsighted. Okay? Now, there's, as this author's trying to say, there's another reason you could be nearsighted, is you could just, the socket of your eye is for some reason just too long. But either way, we would say that the focusing effect of your eye is too strong for the length of your socket. And like I said, I didn't start wearing glasses till my senior year in college. And so I know my socket is fine. I had fine vision for the first 20 years of my life. And it wasn't until then that things changed on me. And so I don't have this problem, but that could be a problem. Most people have this problem. Most people who are nearsighted have this. In fact, most people who wear glasses, at least at a younger age, most people are nearsighted. And your lens is too strong. Now, the reverse effect of this is farsightedness, this hyperopia. And in that case, your lens is too weak. Okay? Now, let me point out that you could, of course, and that's why it's called farsighted, is because if your eyes are relaxed and you're looking at something far away, you're going to go, oh, it's out of focus. But if it's too weak, remember, you could use the muscles and squish the lens and bring it into focus. So somebody who is farsighted is not being relaxed when they look at something far away. They actually use their muscles and make up for the lack of curvature in their cornea and get something far away in focus. So that's why they say, oh, I can see things far away. But the thing is, they've already used some of their squishy power. And so as objects get closer and closer, they squish, and they run out of squishing room early on. And so somebody who's farsighted would say, you know, if they just kind of relaxed and looked far away, they go, oh, it's out of focus. But then they would kind of just, probably without thinking, bring it into focus because they would squish their lens and they go, oh yeah, I can see that road sign. But then as the road sign gets maybe 2 meters away, they've used all their squishiness and they can't squish their lens anymore. And so when things get closer than 2 meters, they're out of luck. They can't see things close. And hence the name farsighted. Because you can see things far away, fine. But you can't see things close. And so it's exactly the opposite of nearsighted. And of course, LASIK surgery can fix that too. They would go in and they would cut and change the shape of the cornea and give it more curvature. Depending on, you know, like I said, it's do you have too much curvature or too little? And so you can reshape the cornea. And assuming your lens is still working fine, you can now have corrected vision. Now, of course, the same thing can be said here, that maybe your eye socket is just shorter than the normal 2 centimeters. That would be the same end-up result. But again, most people who are farsighted have this effect. Most people who are nearsighted have this effect. Which, of course, then brings up the whole question of, okay, so if this is the problem with the eye, how do you correct it? Let's go with the myopia, the nearsighted. I'm nearsighted. How are you going to correct that vision? Well, with another set of lenses. And so you can put on a pair of glasses, or you could put on some contact lenses. Either way, you can use those to make up or to counterbalance the deficit of your cornea. So in this case, this person here being nearsighted is going to put, and notice they put a lens here that diverts the light. Remember we said what's wrong with somebody who is nearsighted is they bend the light too much. So the way to correct it is to put a concave lens. And so looking back at last chapter, what would happen then is if you took the light from a distant object, it would first hit your lens of your glasses and spread out. Fortunately, I don't think that's our building, right? So, some fire alarm. Hopefully they're just testing it. Okay, well, it's not us. Oh, so I'll keep going. But to correct this vision, you would want to get something that spreads the light out. Now, I know we were kind of rushing yesterday, and I showed you this lens where it makes the light converge. Well, if I held it up in front of the screen here, you can kind of see the light from my projector comes in here and makes kind of a spot here because the light comes in, and so there's this round shadow here. So that's the converging lens. The one I didn't get you to show you, although I did hold it up, if you remember, I held this up on the whiteboard where the light came in and spread out. And it's concaved inward. This makes the light spread out. That's the kind of shape you would want. And I've got one like that. It might be hard from your position to see it, but it does curve in both. Ooh. We should really clean our optics with something of quality. But this one curves inward. This one does too. Maybe I'll hold this one up. You can kind of see it. If you remember, we said the one that diverges it, which I showed you in comparison with the mirror. And so the convex mirror made it diverge. Remember, it made something smaller and upright. And so if I kind of hold this in front of my face, you might see my eye, and hopefully my eye looks smaller but upright. And you can kind of see that if I hold it up here. Maybe I even need to get close. Can you see how the light then spreads out bigger than the shadow? In fact, it makes a kind of a shadow in here because the light's not as intense. The light would have just gone straight, but because it hits this lens, it kind of spreads outward. And so something that diverts the light is going to get the shadow from the lens and then a little bright ring around it because the light that was going through that lens spreads out and it goes to the light that is not going through the lens. And so this kind of this ring effect. Whereas something that converges the light is going to bring it to a spot. So you're going to get the shadow of the lens and you won't get any bright spot around it. See, I say all that because it's real easy then to figure out that I'm nearsighted, because if I just hold up my glasses right here, and I'm only a little nearsighted, so maybe I need to hold it back a little bit. But as the light hits, it's going to spread them out. And so as it spreads it out, you'll see it bright with kind of a shadow there. You also kind of see a little pointy thing. That's my astigmatism. We'll talk about that too here. But Ron here is farsighted. So I've got his glasses. And that, if you look, will bring the light in and focus it to a point. It brings it in. Because that's the other picture your author says. You know, how do you correct somebody who is farsighted? You see, the reason they're farsighted is because their lens doesn't bring the light in enough. And so you need a lens that does that to help out with it. And so that's the difference in our vision, a difference in our problems, and the difference then in our correcting of our problems is how we redirect the light before it enters our eyes so we can fix it. Now, when it comes then to doing any calculations, we think of it this way. If you were to ask then, okay, what kind of correction visions do I need? Or since I've got farsighted on here, I'll say, what kind of correctional vision does Ron need here? So Ron being farsighted means that he can see things far away, but not very close. So I don't know what Ron's vision is, but my point is his near point, the things that he can see well near, are not the normal 25 centimeters that I was talking about. His might be 2 meters. So because of that, the corrective lens would do something like this. Let's say he's reading something. Here's the object. He wants to then make an image of it that is further away. So his eyes can focus on it, right? His way of correcting it would be to say, take something that I can't normally focus on that's close, send it through a lens so the lens gives it the appearance of being over 2 meters, because then my eyes can focus on that. And so we need to put a set of lenses on Ron's face that allow him to take anything that's close and give it the appearance of being far away, because that's what his eyes operate on. He's farsighted. Mine's the opposite of that. Mine is back here where I'm nearsighted. So I want to put a lens here so that if I have something far away like this tree, when the light hits the lens, it will give it the appearance of being close, because my eyes can focus on things that are close. And so I have what we would call a far point. I can stand here and look at things. That's clear, that's clear, that's clear. Let me turn this so I can read it. That's clear. Not so clear. And that might be about 2 meters. So my far point is 2 meters. So I want a pair of glasses then, or contacts, that basically say that anything that is more than 2 meters away, like that periodic table, let the light come in, readjust it so that it has the appearance for my eyes as being closer than 2 meters. Now, don't get me wrong, I've learned to wear glasses, and I know that it's not really 2 meters away. I've got used to it. Anybody who's worn glasses know the first time you put on glasses, and again, I was kind of old the first time I wore my glasses, and I was 21, and I'll never forget, then you see it right away. You're like, okay, what's neat about it is I can look at this periodic table, and you put it on, and you go, whoa, why is it so close? I'm glad I can read it, but it's so darn close. And I'll never forget the eye doctor saying, now, and it was on the second story, so he says, okay, now, everybody gets a new pair of glasses. As you go down the stairs, you have to hang on to the rail. And I was like, I'm 21. I haven't touched the side of a rail since I was 5, and I probably won't do it again until I'm 50. Why would I hold on to the rails going down the staircase? Oh, but I got on that staircase, and I looked at those stairs, and they looked like they were this close, and all squished together. And I was like, whoa, okay. Now I see why the doctor told me. And so I carefully go down the stairs. And sure enough, within a couple of hours, no more than one day, my brain got used to it. And now I can look at, a periodic table where technically that periodic table is giving the appearance of being close, but I've gotten used to it, and I know it's not close. It's 15 meters away. I know where that periodic table is. And so now I know my depth perception is fine. I can, drive a car, make a left-hand turn, know how deep things are. But when I first put on my glasses, there was no way I should be driving a car. It just didn't work right. Anyways, but we're going to use that knowledge to answer some questions by saying, okay, what kind of lens should I put on my eye? I would say, since my far point is 2 meters, I need to make it look like something that is really far away is at 2 meters. And everything then is a little bit closer. And in Ron's case, being farsighted, he needs to take things that are close to him and make them look 2 meters or more away. And so that's kind of how we'll do our thinking and do our math here as we get into some examples here. So let me do an example here as correction correcting one of these. Maybe I'll leave this here and say, okay, let's use this same logic. In fact, maybe I'll put this equation here on the board. 1 over the object distance plus 1 over the image distance is 1 over the focal length. Let me also put the magnification as minus the image distance over the object distance. Let me put the power is then the reciprocal of the frequency. And so those are our 3 basic equations, really kind of 2 of them here, that kind of describe the lens system. And so as we go to correct them, what do I need to do? So I thought we would look at a couple of examples, but starting with one directly in the book, and it's example number 3. Oh, I forgot astigmatism. I apologize. Let me go to the next picture. And then there's one other little subtlety that I should touch on here. And this picture is kind of a test of astigmatism. It's just a bunch of lines and kind of a star pattern. But see, the idea here is if your lens is correct, you will have a curve left-right and the same curve up and down. And therefore, when your lens of your eye goes to focus on something, its curvature up and down will be at the same focus as things left and right. But if you have something that has a curve more like a cylinder, you know how a cylinder would have a curve left and right, but not up and down? Do I have anything that looks like a cylinder? How about this coffee mug here, right? So if my lens was shaped this way and had a lot of curvature this way, but very little this way, it would focus the light at a short distance, left and right, but a long distance, top and bottom. And so I would have a hard time having up and down be focused at the same time left and right. And so if you have a asymmetry to the curvature, we call that astigmatism. And it's pretty easy to detect with a bunch of lines that are horizontal, vertical, and at an angle, because if you wear glasses and stand back and look at it, you would go, okay, does any set of those lines look darker and crisper to you? Now, I'm not sure displaying it through this overhead is a good way to do that, but on the printed version, if you've got these lines, and in my case, now that I have my glasses off, I look at this and the line that goes up and down is dark, it's bold. It's in focus for me. It's a little beyond my near point, so if I got a little bit closer, it's really crisp and focused. Right here is about my near point here. So right here, this line is really crisp, but these are kind of fuzzy. Not too bad. And so I would say I have a slight asymmetry, a slight astigmatism. So again, when they build me my glasses, they're going to curve it left and right different than top and bottom. And so there's my astigmatism. And of course it can be different for each eye. And so it's kind of nice to cover one eye and look at it, and then cover the other eye. Because when I look at it with my left eye, yeah, this is nice and crisp, and these are blurry. So the astigmatism must be in this eye. Because when I do this eye, it's much clearer all the way around. There still is a little blurriness here. So there's a small amount of astigmatism in my right eye, but most of my astigmatism is clearly in my left eye. And so what is wrong with my eyes? And so again, they'll correct that and they'll give a different pattern. And maybe I don't know if you've ever gone to the eye doctor, but they put the corrective one and they go, which is better, 1 or 2? And then you say, oh, 2's better. Okay, and then they do it. Then they turn the lens, the astigmatism, and okay, which is better, 1 or 2? And they're trying to find that axis of where your eyes have a little bit of different curvature. So they know how to correct for all that. All right, well, like I said, this is probably a good time then to do some more examples. And you'll see kind of all these words I've been saying, I'll put into practice with some numbers and some calculations. And I think the best one to do that I saw right away was really kind of, even though your author does it, was example number 3 here. And so even though he does it, I think this is worth pointing out here, because it goes on and it says, let's correcting someone who is nearsighted. Okay, so we know somebody has myopia, we know they're nearsighted, we know they're going to need a diverging lens here. Okay, and we say here, what power of lenses is needed to correct the vision of a person who is nearsighted, whose far point, and this is the part I want to emphasize, there's that terminology, far point. What does far point mean? Their far point is 30 centimeters. So again, take off my glasses. Somebody who is nearsighted means they see near. That means they can see up to some furthest point, clearly. That's their far point. And I would say this person's significantly nearsighted. I mean, they can only see things clearly to here, 30 centimeters. Where, like I said, I'm just a little nearsighted, so I can see out to 2 or 3 meters pretty good, but beyond that, things start to get fuzzy. And so, all right, assume that the corrective lenses are held, and this is going to be an important part, held 1.5 centimeters away from the eyes by your eyeglasses. And so this would be the difference between contact lenses and glasses. And so any of you go to the eye doctor regularly or even at all, you'll know that when they give you a prescription, you go in and say, I want a prescription for glasses versus I want a prescription for contact. Because the location of where the lens is a little different. And so we're going to have to factor that in. In fact, I would even say contacts are a little easier to work with because they're right on the lens. There's no difference between the contact lens and the eye lens. But for eyeglasses, there's an extra 1.5 centimeters. And so I'm going to take that into consideration. And that's what I wanted you to see in this problem. Yeah.
Can you just add that to the focal point?
I won't just add it to the focal point, but let's think it through. How about that? Okay. Let's see what I would do with it. All right. All right. So this will give me a chance then to say, physics is about knowing how to apply a few fundamental principles to explain a universal phenomenon. So I'm going to use those same set of equations. The same set of equations. There's nothing new in this chapter about these equations. I'm just going to be using them to apply them to the human eye, and in this case, then, the corrective glasses that go in front of the human eye. But I need to know that it's 1.5 centimeters in front of my eye. All right, so let me get my creative juices going here and say, all right, so what is the power? Now, of course, the author has the solution here, so let me not look at that. Let me just start off by saying, all right, let's think about this equation. Okay. I want to correct my vision. Keep in mind that the person's far point is 30 centimeters. So they can see things 30 centimeters and closer. So the goal here is to say, let's take something that is really, really far away, run the light through a pair of correcting glasses, that's what I want to find, the power of the correcting glasses, and make it look like it's 30 centimeters away, because then the human eye can focus on it. This person's human eye can focus on it. So I would start off this calculation and say, let's look at an object that is really far away. 1 over big. So object distance, big. Okay? And where should the image appear to be from the corrective glasses? Well, as the problem says, we want to make it look like that image is 30 centimeters away from the eye. But remember, the glasses is 1.5 off my face.
So you add it?
So I would subtract it. Right? So if I were to draw a picture, I would say, okay, so here's the eye. And so way over here is this tree I'm looking at. And so that's the big distance away, 1 over big. And I want to put some corrective glasses right here so that it makes an image of the tree so that this distance right here is 30 centimeters. And according to this equation, image distance is from the lens. So I guess I want this distance. And so that would be 28.5 centimeters. And so there's my thinking of how I would correct this person's vision. I would want them to be 28.5 centimeters away. And of course, I'll just do the same thing as we did before. 1 over big is 0. And now I'll just take the reciprocal. Oh, and I guess I made a small error here, and I apologize. This is that part in the last chapter where he said, watch your signs, your pluses and minuses. And so if you start with an object over here, when the image is formed as the light goes through, on this side is a positive image distance, a real image distance. This side is a negative image distance, what we call the virtual one. We called that case number 2 yesterday. So I should have put a negative for the distance, which makes a focal length which is negative. Now if we change that to meters, it's a negative 0.285 meters. And now if we take the reciprocal of that, that'll answer the question of what is the power. So negative 0.285 reciprocal. And so we're looking at a negative 3.5 diopters. And so if this person goes to the eye doctor, they're going to leave the eye doctors with a prescription that says you need glasses, and they're going to give this number. This would be the prescription. You'd have one for the left eye and one for the right eye, but they'd say this corrects, say the left eye, you need a negative 3.5. That's your prescription. So clearly anybody who has a negative must be nearsighted. And of course, anybody who is farsighted must have a positive, because that's the difference in those focal lengths. Remember, again, going back to the last chapter, we got to watch those signs. And the converging lens had a positive focal length. The diverging lens, and that's the one that's correcting the nearsightedness, the diverging one has a negative. So sure enough, that's what your author gets here. It says, okay, negative 3.5. Well, let's try this logic again. Let me try a couple of other ones here. How about number 6 here at the end of the chapter, 1174 should get me near the end. Maybe a little bit more. Where do the problems start here? Let me try number 6. And so number 6 says, what is the far point of a person whose eyes have a relaxed power of 50.5? Okay? So now remember what we did earlier. We said a person who was relaxed would have a power of 50. So this one's a little stronger. Okay? This is a nearsighted person. Which of course is why they say they have a far point, right? I mean, all those words fit together. If you're nearsighted, you can see things near. Your relaxed is too strong. That's why you have a 50.5 instead of a 50. And of course, you have a far point, because what that means, like me, is I can see things up to a certain point. I can't see things any further. I have a far point. I guess technically I have a near point also, but you know, it's less than the 25, so I guess that's the only thing positive about being nearsighted, is as you get old and your lens become less squishy, you already have too much curvature. So many of my friends wear reading glasses. I don't, because I already have built-in reading glasses that make me nearsighted. I don't have that. I have the problem that I have to wear the glasses all the time, not just when I read. Okay, and so although I guess now I take them off and read. So I don't know. Like I said, I don't know if there's any advantage of that. But anyways, I want to find this far point. So again, let's kind of go through this thinking here. Okay, all right, and say, all right, 1 over the object distance plus 1 over the image distance is 1 over the focal length. All right. So what they're saying here in this problem is, what is my far point? So when I relax my eyes, okay, so we'll take off my glasses. I'll relax my eyes, look far away. They're saying here that I have a 1 over f of 50.5 diopters. That's the power of it. So that's the focal length at that particular moment, right? All right, so then I am going to focus then on whatever is the furthest away from me. I want to think this through. So there's my far point. So there's my object distance. So there's what I'm trying to find is right here. What is my object distance? And of course, where the image is formed, okay? And so again, imagine this without the glasses on. And so the image forms on my retina. And so this image distance is then my 2 centimeters. And so there is going to be some mathematics telling me what is the furthest this object is. Okay. And so I have a 50.5 minus a 1 divided by 0.02, and I will take the reciprocal, and it looks like we're looking at about 2 meters. And so this nearsighted person can relax enough of their eye to see out to 2 meters. Well, that's about me. And then I can't relax it any more than that, so things are fuzzier beyond 2 meters. And so that's my far point. All right, well, let's see. I think I wrote down here another fun calculation we could do. Number 9. Number 9 says, in a LASIK vision correction surgery, the power of the patient's eye was increased by 3 diopters. So in other words, this must have been a farsighted person, right? The power was too low. They didn't have enough curvature. And the doctor went in there and said, okay, we've got to increase the power of your lens. We got to increase it by 3 diopters, okay? All right. Assuming this produces normal close vision, what is the patient's near point before the procedure? So again, notice how they say near point? That's confirming what we said earlier, that this is a far-sighted person. This far-sighted person can see things far, but they have a near point. And so what was it? What was this person's near point before the surgery? Okay. So I'm going to take the same logic. I'm going to use the same set of equations, and so maybe I'll leave them on the board. And I'm going to say, let's apply this thinking to the human eye. And so I will put number 9, 1 over the object distance plus 1 over the image distance is 1 over the focal length. And of course, notice the question is asking before surgery. Okay, so before surgery, I would, of course, have a correction or a focal length of 51 diopters. Now, maybe we should stop and repeat what we did earlier on. I've erased it, but earlier on we said if somebody has then normal vision, right, you could look at something that is 25 centimeters away and it would form an image on the retina which is 2 centimeters away. That came out to be a power of 54 diopters. So I'm going to use that information. Maybe if I forgot it, I'll just recalculate it here. So 0.25 reciprocal plus 0.02 reciprocal equals taking the okay, didn't that 0.05 reciprocal plus 0.02 reciprocal equals, oh good, 54, okay. I must have did something wrong in my calculator because I got a different number. I got like 57. I was like, wait, I thought we had got 54 a half hour ago. Okay, so maybe I should have just started there. Let's repeat what we did a half hour ago. Let's say what would be the power that you would need to correct your vision. And so your corrected vision, your eye has to have a power of 54. And I say all that because this is the dead giveaway. When they say you're going to increase it by 3, what you're really saying is your patient, who's farsighted, has a low power, and they must have a power of 51 diopters. Because we want to correct their vision. We want to increase it by 3. All right. So if we think about the patient before the surgery, we know that they have a focal length associated with a power of 51. That might be the hardest part of this problem, is just, okay, where am I going to get the focal length before we correct the vision? And that's where the 3 diopters come in, because we know a corrected vision, a normal vision, has 54 diopters. So I go to correct it, I'll have a 51 diopters. All right, so you would say then, for this individual, before the surgery, this is their focal length, or the reciprocal of their focal length. This is where they would focus it on, and so this right here would be their near point. And so, got a little math to do. But I need to find out then what that point is. So I will take the 51. I will then subtract the 1 divided by 0.05. And I get a, oh, I got to take the reciprocal, sorry. And so I get 1 meter. And so this far-sighted person had a near point of 1 meter. So anything that was 1 meter or beyond, they were fine before they got the surgery, but they couldn't see things closer to that. They needed glasses, and presumably now that they've got their surgery, they can see fine there. All right, well, maybe another one is worth doing here. 22. Says here, oh, and then this would be a good time to take our break. It says here, 22, a mother sees her child's contact prescription and it's 0.75 diopters. Okay, let me start right there. Notice it's positive. What does that tell you? It must be a converging lens. The person must be farsighted. Yeah, so the negative one we got before, the negative 3.5, which I meant to mention then, my prescription is a negative 1.5. So I told you I'm nearsighted. I have a negative number. I'm not very nearsighted, so I'm a negative 1.5. But this patient is farsighted. It's got a positive number. Okay. By the way, maybe as a sub-note here, remember we said that the diverging lens acts like this convex mirror. So it makes things look smaller. I say that because one thing I don't like about being nearsighted, and fortunately I'm not very nearsighted, but when you put this kind of lens in front of somebody's face, of course the nice thing is they can see really well, but what do people see when they look into your eyes? They're then going to see a smaller eye. And there's a psychological effect that people got small eyes, and beady eyes are dangerous and mean. And so people are nearsighted, especially very nearsighted. You just kind of have those small eyes. That's why those Disney characters, Aladdin and Mulan, they all got those big eyes, right? Beauty and the Beast. Even cars. The Imagineers kind of did the first version of cars actually had the eyes as the headlights. And that's how most people kind of think of a car. The headlights are the eyes. And then the engineers at Disney say, oh no, those eyes are way too small. We're not going to make it friendly enough. We're not going to make it happy enough. And so if you've ever watched the movie Cars, you'll see that the artists changed it and the eyes are actually in the windshield. The eyes are huge. And that's the neat thing about being farsighted. Somebody who's farsighted and you look them in the eyes, their eyes look big. They look more approachable. They look a little happier. They don't look so dangerous, if you will. Well, that's only a small effect. So I would much rather wear my glasses so I can see than worry about somebody thinking I was evil eyes. But that can be a psychological effect in there. Anyway, so for this child, it just going to make their eyes pop out, And I know a couple of children. It seems to be children, if they wear glasses at a young age, they tend to be farsighted. I'm not real sure why that is, but I know this one little girl. She's so cute and she's farsighted, and she puts on these glasses. She's got these big, beautiful eyes. They just like, whoa! And it looks so good. Anyways, so back to this. So we're going to do this correction one, and so this is correcting their lens, and it's a farsighted. Oh, it even says farsighted. So mildly farsighted, and the person has a near point of 29. What is the power of the tear layer between the cornea and the lens if the correction is ideal? Take the tear level into account. Oh, I'm sorry, I'm reading the wrong one. I went 22. I got lost in number 20. Okay, let's go back to 22. Sorry. A mother sees her child's contact prescription of 0.75. That's the same one as this. So it's mildly farsighted. Okay, what is the child's near point? Okay, so again, same logic here. So I'm going to come over here, and maybe I'll just put a little number here and say, all right, let's call this number 22. And say 1 over the object distance equals 1 over the image equals 1 over the focal length. And the good part about this is they told me the power of this lens. They told me the reciprocal of the focal length. And it's a positive number, and hence it's farsighted. Now, again, we want to be careful whether we're talking about the corrective lens or the eye. See, because on a couple of these problems, you'll notice that I said the image distance was 2 centimeters. And that's true if I'm talking about the lens of the eye, but if I'm talking about the correcting lens, that's not the image distance. The image distance now is where do I want the image to appear after going through the lens so that then the human eye can take over, right? So in this case, how they say it, the child's near point. And so what we want then, since the child is farsighted, is something that is close to the child, to now appear to be further away so the eye can do the rest of the work. Okay? All right, so what I'm trying to say here is from the corrective lens, we want to take an object that is close to the person. You know, again, maybe they're reading a book. And so we want to make sure that what those contact lenses do is take the object that is now close to the child and make it appear further away. And so this type of lens will do that. And how far away should it be? Well, it should be far enough away to that person's far point, because that's where the human eye can now focus on it. And so that's kind of our logic. All right, well, we should move on to our break here. So let me go ahead and just punch in this number, 0.75, and then minus 0.25 reciprocal, and then take the reciprocal of that. And so we're looking, of course, at a negative 0.307. Now, of course, the negative means it's going to be virtual. And that's perfect. That's exactly what we would want. We, of course, want it to be virtual. We want the image to appear on this side of the contact lenses, right? We don't want it to be on the real side. But then not worrying about the negative here, this individual's far point must have been about 30 centimeters. So, as I said, they're not very far-sighted. They can see all the way up to about 31 centimeters. That's pretty close. Kind of questionable if wearing the glasses is even needed. And for a child, you'd probably say, okay, wear them when you read, but other than that, you don't really need to wear them. All right, well, I hope I didn't say too much, but I did want to kind of emphasize the correction of this is kind of a simple calculation, but I think the thinking about what numbers to put where can be quite challenging. You know, when do you use the focal length? And then my warning for you is you just got to be careful about, are we talking about the corrective part of it, or are we talking about the human eye part of it? But we basically do this calculation. All right, well, I'll say stop. Let's give you guys your 15-minute break, and you guys online, I'll say bye. You can take a break too and come back whenever you want. All right. Hey, everybody. Welcome back for the break here. Let's kind of wrap up this chapter and see how far we get in the next chapter. As I said earlier, we're just going to do as much as optics as we can and then call it quits and call it what it is here. And so moving through this chapter, and I spent most of the time on the understanding the eye and the corrected vision, because I thought that would be useful to you. In fact, I will go to section 3, even though that was the section I said I'm going to skip, and I am going to skip it. I just want to take this as an opportunity that if any of you have extra time, and you probably don't until this semester's over, you're way too busy, but after, you might want to read this section. I think a lot of you would like to read about how our eye detects the different colors and how the rods and the cones work and the sensitivity of the eye and why things are black or why they are red or are they blue. And I think you'll kind of enjoy that. And grayscales and anyways. But let me move on to the third piece of this chapter, which is the section 4, which is the microscope. And I want to emphasize then that for the microscope, the best way to understand a microscope is to really say the same thing that I've been saying this whole chapter, which all comes from the chapter before, that I'm just going to apply 1 over the object distance plus 1 over the image distance equals 1 over the focal length. And that the magnification is minus the image distance over the object distance, and the power is 1 over f. And so those are the 3 equations you saw me using when we talked about the eye, when we talked about how to correct for vision problems with the eye, and it's also what I'm going to use for a microscope, and if we had time, I would use for a telescope. And so this is my chance to say again, it's a few fundamental principles that explain a universal phenomenon. So if you really want to get a good handle, and I'm sure you do before the test, on this chapter 26 and the last chapter 25, it's understand this set of equations. I mean, it's not very easy, but once you get there, you can understand all the applications. And so, like I said, the human eye, the camera, the corrective vision, and now we're the microscope, and I'll just kind of point out the same thing. Section 5 is the telescope, and so again, some of you who might have extra time after this semester, you might want to look at Section 5. And so Section 3 and Section 5 are ones we're not going to have time to cover, but they really are just doing this. All right, so the best way to look at a microscope and the best way to teach it is to actually run through a calculation. And so I'll show a little diagram here of a microscope, and we often call this a compound microscope because it's actually using two lenses. And so what you do is you take an object, and of course if you're using a microscope, the object is usually pretty small, and the job of the optics is to make it bigger. But it is also, as we just said, part of the microscope is to make it look kind of far away, at least beyond 25 centimeters, because remember, the human eye focuses really on things at 25 centimeters or greater. And so the microscope basically does this. There is this first lens, which we call the objective lens. And so you put your sample right at the end or right at the edge of your objective lens. And so maybe this is the objective lens, and maybe this little bug right here is what I want to do. So my first lens would go right there. So we call that the objective lens because it's really close to the object we're trying to look at. And of course it would make then an image maybe right, say here, because then I will take a second lens. And of course, making an object right here is what we called case number 1 back in chapter 25. So I've got a real image right here. And then I'll use this for case number 2. I will take this called the eyepiece, and I will make it so that the image from number 1, the object lens, now becomes the object for the eyepiece. And then I can kind of adjust where it is and create what we call case number 2, a virtual image. That makes things bigger, upright, further away. And so as we look into it, appearing to be further away, greater than 25 centimeters is our point. And so when we talk about a microscope, we are going to get a magnification for 2 reasons. The first lens, so right here, the objective lens is going to take the object, it's going to make case number 1, so it's going to turn it upside down, and it's going to place it right here. So then the eyepiece, you're going to take the object, or I should say the image from the first one now becomes the object for the second lens. And so what this is saying is here's the focal length of the eyepiece, and notice then that this, which is the image from the first lens, which I'm now going to call the object for the second lens, is inside of the focal length. That's what we call case number 2. And case number 2 makes a virtual image. It does not invert it. So I guess I would say it's already inverted, so the second lens keeps it inverted. And that's what they're trying to show in this picture. So they say this is the final image. So the final image has been magnified twice. And so if you want to know how much bigger the final image is, you have to take the magnification of the 2 pieces. And so that's going to be kind of my first equation I'm going to say here. So the magnification total is the magnification, and I'll put an O. So it's the magnification of the objective lens. And then it's the magnification, and I'll put an E for the eyepiece. And so basically what I'm trying to say for a microscope, and if we had time to do the telescope, I would say the same thing, that we're just going to apply this set of equations twice, because we're going to have 2 lenses. And for the second lens, the object of the second lens is the image from the first one. And so that's kind of the best thing I can say, is that unlike a simple lens, which we usually just call a magnifying glass, I have a much better situation. So a microscope is much better than a magnifying glass. Not only can it magnify more, because the total magnification is the two lenses together, but it also takes and kind of moves the object away, far away, so it's kind of in a more useful approach for my eye. Sadly, the negative thing about it, and I'm going to trust that some of you, many of you, you've done the labs looking in the microscope, you'll notice that what you're looking at is backwards. Now, if you're just looking at some bacterium, you don't really notice it. You're just looking at the bacterium and you go, oh yeah, it's crawling this way. But if it crawls and starts to go off the screen, you have a tendency to move your slide that way, and you'll notice when you, went the wrong way. And so as you're looking in the microscope and you want to make your image move to the left, you have to take your slide and move it to the right. And it takes a little experience at first to get kind of the knack for that. You go, oh, wow, that's true. It moves it the other way. And so they're backwards. In fact, I came across this not recently. I know we're not talking about the telescope, but the telescope can do the same thing. And I was looking at Mars, and I said to whoever who I was with, I said, you could just make out a small white cap at about the 7 o'clock position. And they were looking at it with high-powered binoculars, which don't invert. And they're looking at 7 o'clock position on a, and they're like, I don't see anything. I see something at 1 o'clock. Kind of sounds like you're describing, but I don't see anything at 7 o'clock. And then it dawned on me, oh yeah. I'm looking at the reverse. It really is the 1 o'clock. You're looking at it right, but I've got this backwards image. Anyways, so you can kind of see that in there. And so I think the best way to run through the microscope is to actually just run through an example and say, let's watch this and let's see it play out. And so problem number 30 is exactly that. And so let me jump down here to problem number 30. Whoops, that was a little far. And say, all right, well, let's put this into, or my words into action. And so let me again just think of it as two lenses, and I will just apply this equation twice. So number 30 says you have an amoeba that is 0.305 centimeters away from a 0.3 centimeter focal length objective lens and a microscope. And then it's multiple parts, kind of helps you work through the problem. A, where is the image formed by the objective lens? Now, to kind of help me understand what's going on, I'm going to draw the two lenses and say, all right, I'm looking at this little amoeba, and I'll just draw an arrowhead in place of this little amoeba. And I would say then my first step is just to worry about the first lens. What happens to the light as it goes through the objective lens? And that's the first question. It says, where is the image formed by the objective lens? So if I go 1 over object distance plus 1 over image distance equals 1 over focal length, I could then write this as the reciprocal of the focal length minus the reciprocal of the object distance equals 1 over the image distance. So if I then take the reciprocal of all of that, I get my image distance. All right, so let me take the focal length and take its reciprocal. So it is 0.3, and then I'll hit the reciprocal key. I will then subtract off the 0.305 reciprocal, hit enter, and then take the reciprocal of that. All right, now I did my units in, I think those were all centimeters, weren't they? Centimeters. So this comes out to be 18.3 centimeters. And so if you've worked with a microscope, you know that you put your object really close to the very end or the tip of the microscope. That slide is really close. In fact, they even give, it's less than a centimeter. It's only 3 millimeters away from the tip of the microscope. And so what it's saying is you are going to get an inverted real image. This is, the optics from the last chapter. In fact, we could even ask how big it is or how much it is magnified, and I think that is actually the next question, part B. Let's see. Part B, what is the image magnification? And again, I think just from the object piece. So this would be 18.3 centimeters. And the object distance was I believe I said 305 here. They need this 3.05. All right, so if I grab my calculator, take the 18.3 and divide it by 0.305, we're looking at a magnification of negative 60. So as I'm trying to draw with my picture and the author had in their picture, I would say this first step is the image is 60 times bigger. So that helps me see this little tiny amoeba, it's 60 times bigger from that alone. Of course, now the problem continues. So I guess I'll call this A and I'll call this B, and maybe then going all the way over here to C. We can now begin to ask what happens as the light enters the second lens. And so C says an eyepiece with a 2 centimeters focal length is then placed 20 centimeters from the objective lens. Okay, so typical microscope, you have your 2 lenses. And so down here near the object, the slide, if you will, I have my objective lens. I got my eyepiece right here, and they're saying there's 20 centimeters between here. And so if I put that into my picture, they're saying this whole distance between the 2 lenses is 20 centimeters. And so I need to read that carefully here, because it says where is then the final image? And I would call the final image then the image after it goes through the second lens. All right. So I need to do this calculation again. The 1 over the object distance plus 1 over the image distance, 1 over the focal length, which, as we said earlier, you could take the reciprocal of the focal length, subtract off the reciprocal of the object distance, take the reciprocal of that, and that's how you get the image distance. And that would be from the eyepiece. And working in things in centimeters, this, they said the focal length for the eyepiece is 2 centimeters. The one I want to be careful with, and this is where understanding the picture and the question makes the hard part, it's not really so much the math, it is what does each of these symbols mean in this equation? And so for the second lens, this is the object distance. This is what I was trying to say. The distance, or maybe I should put it this way, the image formed from the first lens now acts as the object for the second lens. And so the whole reason we called it an image is the light is as if it is coming from that. So as we get to the second lens, we can just say, okay, don't worry about the first lens. Don't worry about the original object. All I've got to do is to say, what does the light do when it hits the second lens? And so this distance right here. Now, you'll remember in our first calculation A, we said this was 18.3. So you have to make sure you interpret and understand what did I just calculate? What did that mean? Well, it meant the image distance. It meant the image distance from the first lens. So, of course, if this is 18.3, that must make this 1.7. See, because the total has to be 20. So if I go 20 and I subtract 18.3, I get 1.7. Oh, by the way, notice that then the distance that and I'll call this the object now. It's actually the image from the first lens, but it's now the object for the second lens. But notice that number, 1.7, is less than the focal length of 2. This is the case number 2, right, from the last chapter. Case number 2 says if you want to make a magnified, non-inverted image, or in this case it's already inverted, so remain inverted, you need to put the object closer than the focal length. The things further out than the focal length make real images and make them upside down. They invert them. But when they're closer, they make virtual images. And that's actually really good because the human who's looking in this microscope is right here. You know, they've got kind of ear and some kind of nose and some kind of mouth and some kind of eye. And we don't want to get it too close. And so we want this second lens to do two things. We want one, to make it even bigger than it was before, so we get a total magnification. And two, we want it to be farther than 25 centimeters away. The further the better. Our eyes can be more relaxed. Nobody wants to look at a microscope for hours after hours and end up with a headache at the end of it. And so we want to relax those muscles, and we want it to get far away here. So that then is where this comes in. Where is the final image? So after thinking about the construction of the microscope, I then know that this object distance is 1.7 away. So now it's an easy calculation. So I'll say it again. I think the calculations aren't too bad. They do have some reciprocals in them. That can be challenging. But maybe more challenging is, where do I get that 1.7? You know, understanding what was meant by this 18.3. Okay, so if I go 2 reciprocal minus 1.7 reciprocal, enter, hit reciprocal, I get a distance of a negative 11.3. And so that means it's going to be 11.3 away from the eyepiece. Which I'm a little bothered. That's not greater than 25. So this person's going to squint really hard looking at the way this is panning out. I guess depending how close their eye is to the eyepiece, but usually you're only no less than a centimeter. So they're going to have to work really, really hard and probably get a headache after they spend 3 hours in lab trying to study this specimen here. Makes me think I did a calculation wrong, but I think that looks about right. Now, the magnification then, and maybe at this point I'll call it magnification sub E. This is the magnification of then the eyepiece. Would be then the negative of the negative 11.3. And then the 1.7 is the object distance. And so this is a magnification of about 6 2/3. And so I think the next part of this question says, okay, so what is the total effect of both of these lenses? And so you would take a 60 times magnification and a 6.67. And so we're looking at 400. Now I guess technically it's a negative 60, so maybe I'll put a negative 400. So the good news is this has magnified the amoeba quite a bit, 400 times. It's 400 times bigger. Makes it easy to see this little tiny single cell organism doing its thing and kind of studying it and learning a little bit about life. But the negative means, of course, it's backwards. Of course, you don't care. You just see it moving. So whether it moves left to right or right to left, up or down, doesn't really matter until you start moving your slide and you go, oh, wait, I want to follow it as it's moving. And so I want to keep watching it. And so there's the like I said, probably the best way to talk about a microscope is that way. So with that said, I'll shift gears. Let's go into chapter 27 and let me pull out a few of the principles of our optics from 27. And I might have to modify it a little bit from what I said 2 hours ago when we started here, because I don't think we'll be able to really cover all those sections I listed. And so during the break, I was thinking about this, and I said, you know what I'm going to do is section 8 first. And hopefully I can do section 8 and maybe even sections 3 and 4, okay? But section 8 really is, and again, like a lot of these, it's probably best to draw a picture. Actually, it's probably best for me to call up a picture. It's what we call the polarization of light. And so a very useful property here, the polarization of light, is to remind you of something we said back in chapter 24, that light is a form of electromagnetic waves. And so taking your attention back to chapter 24, but then using this fancy word called polarization, maybe I should put it on the board here, polarization. I think I have an extra I in there. No? I-Z-A-T-O-N. Polarization, as the name tends to imply, is just saying that there's got to be a direction to these electric fields. And so what we call the polarization is that direction. Let me just remind you back in chapter 24. You might remember a couple lectures ago I was standing right here and I was saying, okay, an electromagnetic wave looks like this. You got to think about it in 3 dimensions. The electric field makes the magnetic field, and the magnetic field makes the electric field, and then those propagate and move, and all 3 of those have all the X, Y, and Z axis in 3-dimensional space. And so if it's moving towards me at the speed of light, I'll call this the X axis. And so the energy moves towards me on the x-axis. And then in this diagram, they're trying to show the electric field on the y-axis. And they're trying to show the magnetic field on the z-axis. And so that's the same thing we said in chapter 24. And so let's, I'm going to just use this as an opportunity to remind you what I think you already know, that to picture these as waves, you got to think in 3 dimensions. You will have the motion they move, x. You will have a motion of the electric field, and you will have a direction to the magnetic field. And what we're going to say then is something is polarized. What we mean by that is there's a direction to the electric field. And that's how we'll label it. We could have picked the direction of the magnetic field because we know they're perpendicular to each other. But in that picture, I would say the polarization is in the y direction. And so I would say that my light has a particular polarization, a particular direction for the electric field. Now, please understand, it doesn't have to be in the y direction. I don't have a good picture of this, but it could have been this way. It could have been that the electric field was in the z direction and the magnetic field in the y direction, and the energy still moving along in the x direction. The only requirement is that we have our three axes. And I want you to see that for a given wave traveling in the x direction, it can have one or the other polarizations. The electric field can be either x or y. It could be either y or z. And so I'm going to say that for a wave that then travels in the x direction, we've got two options here. Now, this is one of those things that goes really back to our electricity and magnetism. It's just really too bad humans can't see electric fields. Because it would be so much easier to learn and so much easier to teach and so much easier to understand if our eyes actually detected those. But we don't. Now, of course, we have equipment that measures it, and so as we try to understand science, we kind of learn this through indirect ways. But what's really, really nice about this are things like this. This picture down here says, kind of in an analogy, says, well, what if you made waves on a string, a rope? And so they've got this person here, and they're saying the same thing happens with a rope. If I tied a rope to that wall over here, and I pulled it real tight, and I was trying to make waves go in that direction, in the x direction, I could make my hand go up and down like this. And so you would see these humps in a vertical way, and they would move along. But I could just as easily make waves like this in a horizontal direction. And so the humps would be coming out towards you guys, and they would be flowing this way. And that's what this picture is trying to show. And so this person could make waves. They would be polarized. They could make vertical humps, or they could make horizontal humps. They've got two options. Both of them make energy flow down the string, down the x-axis. But here's what's kind of interesting. What if you put some kind of blocking mechanism on the other end? This just shows kind of a rectangular opening on the other end. See, how you align that rectangular opening is important. See, because this one right here, where the person is making humps in a vertical way, if I took like a barbecue grill and I tucked the string through it, if you make the waves up and down, since the metal poles on the barbecue are up and down, those waves would go right through that opening. It's like you don't even have this metal grill in front of it. However, if I continue to hold this metal grill with the bars vertical, and this person over here is shaking it left and right, then as those waves approach the grill, again, because the bars are vertical, they would stop them. They would not go through the barbecue grill. And so this is what this picture is trying to give you, a visual representation that one polarization will go through, the other will not. Now, that same analogy works really well then for light waves. And so you could see it a little better. I'm going to take just a random light bulb, and so I'm going to use this old school overhead here. And I'm going to turn it on and shine the light here on the screen. And this light bulb is made out of a tungsten filament that has billions and billions of atoms. And some of them are shaking up and down, and some of them are left and right. So what ends up on the screen right here is a combination where half of them are up and down and half of them are left and right. But I have, in this little box here, some material that acts a lot like that barbecue grill I was talking about. On a microscopic scale, these molecules are long, thin chains. So if I were to take one of these and place it on here, you see how it got darker? It's maybe about half as bright. See, the reason it's half as bright is because this one right here is only letting those light beams that are shaking in a vertical direction through, not the ones that are horizontal. But this, like I said, this light has about equal of both numbers. And so I put that on and we cut it to about 1/2. Here's where, though, it can be very interesting. Take a second barbecue grill. And if I lay that barbecue grill kind of in the same direction, there's not much effect. But what if I turn the grill sideways a little bit? What if I turn the barbecue grill 90 degrees? What do I get? And so this polarizing filter is what we call it, is kind of selecting how much actually gets through. You see, if you think that after it goes through the first filter, I only have this much or this polarization. If I maybe switch colors here and tell you that I'm going to set my second barbecue grill at an angle, okay? So in other words, my first one, I would say, didn't do much. My first one was just making sure that I had light that was polarized in one given direction. It's the second one that's kind of interesting, because if I set it at a small angle, and so let's call this angle theta, and now we're going to have to go back to our vectors. But you can think of this electric field as being made out of a component that is along the direction of the second barbecue grill and perpendicular. And the part that gets through would then be reduced by a factor of cosine theta. Now, maybe one more step should be made here, because as we go back to our chapter on electromagnetic waves, chapter 24, we said the energy was proportional to the field squared. So what that would mean mathematically is that if the intensity is coming towards my polarizing sheet, so let me call it I naught. And to illustrate it, let me come back over here to my overhead. Let me take this away. Okay. So there is what I would call I naught. This is the intensity of the polarized light. Now again, please keep in mind, I know in this problem I have two, but I'm just going to say I'm only using this first one kind of just to make sure I have polarized light. And so I really want to focus your attention on what does this one do? This one just makes sure I have polarized light. But this one, depending on how I align it, depending on this angle, I can let a lot of light, a little bit of light, or if I go 90 degrees, none of the light through. And so I would say how much light comes through depends on that angle, and I would even say the square of the cosine, because using our vectors, the amount of electric field is cosine squared. Energy is the field squared. So we're going to have to take the cosine and square it. So if I take the original energy and then have a component, cosine, and a component squared, this would tell me how much energy gets through. Yeah. Right, so again, looking at the math or looking at the grill, if you turn this 90 degrees, how much of this vertical component is horizontal? None. Or put another way, what is cosine of 90 degrees? None. Zero. And so that's why putting it this way will block all the light. Putting it less and less and less and less and less will allow more and more light to come through. Now, in terms of applications, this could be really, really powerful, because what it means is we can control what kind of light, how much light gets through by taking advantage of this polarization effect, even if we can't see it with our eyes. I will demonstrate. Have you ever gone to a 3D movie? And you get these cool glasses to wear during the show? You're like, yeah, look at these great glasses. Why do you wear them? What's the point of this? Well, the engineers have realized that, whoops. So again, I'm going to use this first one to make sure the light coming out is already polarized. And if I place this on here, hopefully you'll see something quite interesting. You will see that this one right here, so I guess the left eye, the light goes through, but it's blocked. That's because these have polarizing filters. This left eye lets vertical stuff through. This one lets horizontal stuff through. Remember, this first one blocked all the horizontal. The only thing coming from this filter is vertical. So the only thing that's going to get through is right here, the left eye. But if I turn my polarizer this way, now this is only letting light horizontally polarized. And watch the reverse. And so the engineers are using this to select the light that you see in each eye. And it's different. Why do you have binocular vision? because what your left eye sees is slightly different than your right eye. And so the three-dimensional image is made because there's a camera or cameras that are projecting an image on the screen, and they're doing two images. One of those is supposed to go to your left eye, and the other one is supposed to go to your right eye. And the way they can filter that out is they would give one image a certain polarization, and the other image the opposite polarization. Of course, your eyes can't see it, so if you just look at the screen without these fancy glasses, you're going to see what looks like a blur, because there's actually two images up there. But when you put on the fancy glasses, one of the images goes to your left eye, and the other image goes to your right eye. And so, in this case, everything that's polarized horizontally goes to my left eye. And then if I turn this, everything that is polarized vertically goes to my other eye, which is great until, if you're like me, I get fascinated with it. So I forget about the movie, and I'm just always taking my glasses off. Oh yeah, there's two images. Okay, that's the left one. Oh, that's the right one. Okay. Let me borrow your glasses, and then I'll compare the two glasses and try them on. Or worse still, that means this is supposed to go to my left eye, but if I watch the movie like this, what should have gone to my left eye now goes to my right eye, and everything just looks weird because it just doesn't have the right depth perception. That's supposed to go to my left eye, now it's going to my right eye, and so you can kind of trick the system. Now I should say, fortunately, they've worked around that, and these newer glasses, we won't have time to discuss them, does something a little different, but they still have light going to the left and to the right. In fact, I like to do this for students. If I turn this display back on, and maybe I find a little white spot on the screen here. There's a big white space right here. We call it white because what's coming out of this monitor is a red color, a green color, and a blue color. Now, it's not all the colors, it's just red, green, and blue, but it's enough that when it enters your eyes go, okay, wait, and it stimulates all the nerve endings, and you're like, oh, that's white. Okay. But how do the engineers control the light? How do they make how much is red, how much is blue? They make a little image out of red and an image of blue and an image of green, and they mix them all together and they come shooting out. And I will tell you, they do that because the different lights are polarized differently. And so I have red, green, and blue coming right here. What happens if I put this in front of the screen? I'm hoping you see green, because I know that the engineers have made green light horizontally polarized. They've made the red and blue vertically polarized. This sheet only lets horizontal through, blocks vertical. So it blocks the red and it blocks the blue, but it lets the green. If I were to turn it the other way, it'll look magenta because it's blocking the green, but it's letting the red and the blue through, but blocking the green. Well, let me do an example, and then we're just going to have to call it quits to the end of our optics, and that only thing I guess we'll do from this chapter is the polarization. So maybe I should tell you guys and the people online here, the only thing I can really test you on, and so I will test you on for Monday's test, is how much energy comes through after it goes through a polarizing sheet. And so all we really need to know is then what is that angle between the direction of the polarized light, so right here, the electric field, and the direction of the polarizing sheet, what we call the transmitting axis. And then we just got to punch in the mathematics. So I wrote down an example, actually two. Let me try 48 and 47 if we have time to do both of those. And I'll come back here and maybe I'll make it a little smaller so we can kind of get to the problems real quick. And see if I can get to, I think I made it too small. Oh, there it is. Looks like 84 is kind of what I selected here. All right, so let's try this one and say, all right, what angle would be needed between the direction of the polarized light and the axis of the polarizing filter in order to cut the intensity into half? All right, well, let me grab my marker, let me grab my calculator. What they're saying here is they want me to set this at some angle so that the intensity that's coming in is then cut in half as it goes out. So I can control the amount of light, and then if I divide it by colors, I can control the amount of color this way. And so I'm going to control how much light. That apparently cut it down to half. So maybe I'm going to take a white screen, maybe cut out half the blue, and that'll make it look pink. So somewhere in here I want to make pink. To make pink, I'm going to take all that white, I'm going to block out half the blue, and I'm going to get roughly a pink color. Okay, so I'm going to come over here and say this intensity is 1/2 of the original. And my goal is to find that angle. What angle do I need to set that polarizing sheet? The good news is it has the initial intensity, so it doesn't matter if it was a lot of light or a little light, it still cuts it in half. I guess I'm going to need to take the square root, so let me start there. The square root of 1/2 should be 0.707, and so that would be cosine of theta. And let me just check that I'm in degrees still. All right, I am. And now let me go inverse cosine, and it looks like an angle of 45 degrees. So set it at 45 degrees and half the light will get blocked and half of it will go through. Why don't we try number 87 as the second one, and then we'll have to call it quits for our optics. Sadly, there's some neat stuff here, but just too much. Try to cover in such a fast pace here. All right, so 87 says, what angle would the axis of the polarizing filter need to make with the direction of the polarized light of intensity 1 kilowatt per square meter, and then you reduce it down to 10 watts per square meter? All right, it's kind of the same problem because we're starting here with 1 kilowatt per square meter. We're going to set some angle between the direction of the polarization and the polarizing sheet, and it's going to reduce it down to 10 watts per square meter. And so maybe the first thing is I will cancel off the units, and then the kilo I will write as 1,000. And so this becomes 1/100 equals cosine squared. I'll then take the square root, and I get 1/10, which is 0.1. And so I can now get this angle by taking inverse cosine of inverse cosine of 0.1. And it looks like 84.3 degrees should be the angle. And hopefully that kind of makes sense, because remember we said if you did it all the way, if you crossed them, you did 90 degrees, you would get no intensity. And we just said 45 would give you half. Well, we're talking about a significant reduction down to 1/100th of the intensity. So we got to get an angle that's getting somewhat close to 90 degrees. And so I'll wrap it up here with our optics and say, okay, this is the last we'll do before you guys take the exam on either Monday or Tuesday, whichever day you choose. And in terms of this chapter, this is all I'll really test you from. And so we lightly touched in chapter 27. But either way, we're going to say we're done with the optics. And so on Monday, as you guys already saw, I already sent out the lesson plan for Monday after the test. And you'll see it says week 5, day 1. Well, day 0 explains it, and then day 1 has the lecture. And that's our first step into our last little unit, modern physics. All right. Well, I'll call it quits and say bye to you guys, and